So you're maybe someone who wants to get a quick handle on some of these big ideas, changing fields like physics, chemistry, material science. Engineering, too.
Right.
You want to sort of cut through the jargon, understand the basics, the what, the why, the how these things are actually used.
Exactly.
Well, if that sounds like you, you're definitely in the right place.
Today, we're doing a deep dive into density functional theory, usually called DFT.
That's right. DFT is this, well, it's a really powerful computational method. It lets us predict and explore the properties of all sorts of things.
Like what sort of things?
Everything from, single molecules up to complex solids and even the places where different materials meet interfaces, which are super important. It's a way to understand the fundamental building blocks of stuff around us.
Okay, so DFT, it's a method used across these really cutting-edge fields. But what's it fundamentally trying to do? What's the core problem it addresses? Well, the main goal, really, is to predict and study the essential properties of these things, molecules, solids, material interfaces. The book we're basing this on today, Density Functional Theory, A Practical Introduction by Scholl and Steckel.
Yeah.
It's really aimed at people who might have a background in chemistry, physics, engineering, maybe math, but are new to DFT itself.
Okay.
They need to understand it, but more importantly, apply it. It's all about taking this powerful tool and making it, practical, usable.
So this isn't just for high-level theorists. This book is actually for the people designing new materials or figuring out chemical reactions.
Precisely. The authors really zero in on people needing a hands-on grasp, especially of plane wave DFT methods. Those are used a lot in research and industry.
Plane wave DFT.
Yeah, it's a specific, very common approach. They want to get grad students, postdocs, professionals, basically anyone who needs it, comfortable actually doing the calculations and knowing what the results mean.
All right, so we know who it's for, the general aim. But what's the big idea behind DFT? What makes it different from, say, older methods?
Yeah.
What's the key shift?
Okay, this is where it gets really cool. Imagine you're trying to describe a molecule, maybe one with tons of electrons. Traditionally, you'd need these incredibly complicated things called wave functions.
Right, I've heard of those. They sound intense.
They are very complex math describing each electron. What DFT does is offer a much smarter way. It shifts the focus to something called the electron density.
Electron density, so just where the electrons are.
Essentially, yes. Instead of tracking every single complex wave function, DFT tells us that all the vital information, the system's energy, its structure, its properties, you can get all of that just from knowing how the electrons are distributed in space. Their density.
Whoa.
It's a huge conceptual leap. This simplification lets us tackle problems that were just computationally impossible not that long ago. It's really opened doors for discovering new materials.
That really does sound like a game changer. Moving from those super complex wave functions to just a map of electron locations.
It's a profound shift. Now, obviously, there's some serious theory behind it to make it work. The book covers this, things like exchange correlation functionals and the Hohenberg-Kohn theorems.
Okay, theorems sound intimidating.
They can be, but think of them as the mathematical proof, the guarantee that this electron density approach actually works, that it contains all the necessary information. They're the foundation. But the book, thankfully, explains them in a way that's, understandable without needing a PhD in theoretical physics.
Okay, good. So the solid theory is there, but the focus stays practical. Now, I always like to see how these ideas play out in the real world. The book summary mentions some examples.
Absolutely. And what's really striking is just how broad the applications are. The book's table of contents, for instance, mentions ammonia synthesis.
Ammonia?
Yeah.
Like for fertilizer?
Exactly. A massively important industrial process feeds a huge chunk of the world.
Wow.
DFT can actually help understand the chemical reactions happening on the catalyst surface at an atomic level.
Wow.
And understanding that could lead to designing better, more efficient catalysts. So yeah, it has very real-world implications. That's a major application showing how practical this framework can be.
So it's not just understanding tiny particles. It could genuinely help improve things like food production. That's significant.
Yeah, it really is. Another example mentioned is metal embrittlement.
When metals get brittle and break easily.
Right. DFT lets researchers zoom in and see how impurities, or maybe something in the environment, affects the bonds between the metal atoms, causing that weakness. Understanding that fundamentally helps in developing stronger, more reliable materials.
Okay, that makes sense. But then it also mentions planetary formation. That seems like a totally different ballpark. How does DFT connect there?
Well, if you think bigger picture, DFT can even give insights into how planets form. Researchers use it to study materials under the kind of extreme pressures and temperatures you find deep inside planets.
Ah, okay. Simulating those extreme conditions.
Exactly. Modeling their behavior helps us figure out how planets might have formed and evolved over time. So you have ammonia synthesis, metal failure, planet formation. These really different examples show just how versatile DFT is. It spans a huge range of science.
Okay, it's clearly got tangible impact. Now, the title is A Practical Introduction. So let's talk about that practical side. If I pick up this book, what does the how-to actually look like?
That's a great question. How do you do a DFT calculation? The book really digs into this. It has worked examples, exercises in each chapter, which is key for really learning it, right? You're not just reading, you're doing.
Hands-on stuff.
Definitely. It covers the basic steps for setting up calculations for different systems, simple solids, surfaces, interfaces, molecules. And it gets into essential practical details, like periodic boundary conditions.
What are those?
Okay, imagine simulating just a tiny piece of a crystal. To make it behave like it's infinite, which a real crystal essentially is, you use these periodic boundary conditions. You basically tell the calculation that the edge wraps around an atom going out, one side comes back in the other.
Ah, so it eliminates weird edge effects from your tiny simulation box.
Precisely. It also covers things like K-point sampling. In crystals, electrons have different energies based on their momentum related to these K-points. You need to sample enough of these points to get an accurate overall electronic picture.
Okay.
And things like energy cutoffs, how much detail you need in the calculation and geometry optimization. That's using DFT to find the most stable arrangement of atoms, their lowest energy state, where they naturally want to sit.
So it really walks you through the settings and steps for running these simulations properly.
That's the idea. It doesn't really tie itself to one specific software program, which is good. Instead, it gives you the fundamental knowledge of the parameters, the concepts, so you can then apply that understanding to whatever DFT code you end up using. The goal is to empower you not just to push the buttons, but to understand what the calculation is doing and what the results actually mean.
That definitely makes it sound less like a mysterious black box. Now, I know there's a second edition out. What changed? What's new in that version?
Yeah, the second edition brings things up to date because the field moves fast, you know? One big update is more discussion on the accuracy of DFT calculations. That's always super important. How reliable are the numbers?
Good point.
It also expands on choosing the right exchange correlation functional. That choice can really affect your results, so understanding the options and trade-offs is crucial.
So it helps you judge how good your answer is and how to pick the best method for your specific problem.
Exactly. It's about making informed choices. Plus, the second edition adds an overview of the different DFT software packages available now. Really helpful if you're just starting and wondering what tool to use.
That'd be useful.
And it includes examples of high-throughput calculations. This is a big area now using DFT to screen tons of potential materials really quickly for specific jobs, like finding new battery materials or better catalysts.
So automating the search for new materials using DFT.
Kind of, yeah. Speeding it up dramatically. And for people ready for more advanced stuff, it now touches on dispersion-corrected DFT.
Which is for?
That's important for systems where weak forces, called van der Waals forces, are important. Standard DFT sometimes misses those. Also, DFT plus U for materials where electrons strongly interact, and time-dependent DFT, or TDDFT, for looking at how systems respond to light, like their color or optical properties.
Okay. Sounds like the second edition really keeps pace with where DFT is heading and gives users a broader set of tools. So wrapping this up, what's the main takeaway message about this book? What gap is it filling?
I think it really aims to bridge the gap between the, let's face it, often pretty complex theory behind DFT and the practical needs of researchers out there in various fields. It gets that a lot of people need DFT as a tool, maybe even a standard tool, but might get bogged down by purely theoretical texts.
So it's about democratization in a way, making this powerful method more accessible to more scientists and engineers.
Exactly. It gives you enough theory to understand what you're doing, the principles involved, but the main thrust is practical, equipping you with the skills to actually start doing DFT calculations. It's meant to be a starting point, a launch pad.
And if you want to go deeper into theory later,
then it points you in the right direction. It's just further readings if you want to explore the theoretical underpinnings more thoroughly.
Okay, so bottom line. If you're working in areas touching materials, molecules across a whole range of science and engineering, density functional theory is, well, it's a pretty essential computational tool these days.
It really is.
In this book, Density Functional Theory, A practical introduction sounds like a great way in, focusing on the how-to while still giving you the why.
That's the core idea, yeah. DFT isn't just some abstract theory anymore. It's a practical, increasingly accessible method, and this book is really designed to empower you, the listener perhaps, to start using it in your own work or studies.
So maybe a final thought for you listening. As you think about the problems in your own field, whatever that might be, just consider how these computational tools like DFT are fundamentally changing how we understand and even design materials and molecules at the most basic level. Could simulating things atom by atom unlock something new in your area? We talked about ammonia, metals, even planets. Maybe those are just the beginning. What other big challenges could we tackle with a deeper, computationally driven understanding of materials? It's definitely something powerful to think about.